Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to step into deep waters, the fundamental theorem of calculus, part 1. And there are two parts to this theorem, and they're both very powerful. So let's go ahead and introduce ourselves to probably the most important theorem in all of calculus. Here it is, part 1. Part 2 is also incredibly important, but we're going to focus on part 1 first. And this, if you didn't watch the video before this, I highly recommend you do that because that is the justification for what you're about to see. If f is a continuous function on a closed interval from a to b, and capital F of x is defined to be the integral function of little f of t from t equals a to t equals x, where x is any number between a and b, and sorry for my screen, it does that, then capital F must be continuous. So let's first kind of settle with that. Capital F, this integral function right here, it's going to be a continuous function. As long as little f is continuous on the closed interval a to b, then capital F is also continuous on the closed interval from a to b. Remember, capital F is telling us the area underneath the curve at little f from x equals a, or t equals a, really, to t equals x. And capital F is also going to be differentiable on the open interval from a to b. But the most important thing is that capital F prime is little f. That is, capital F right there is the antiderivative or an antiderivative of little f. So that capital F is an antiderivative of that little f. It's a very powerful statement because we're tying together old with new, the old being derivatives and the new being definite integrals. A better way to say that, at least this theorem, is that the derivative of capital F, which is the derivative of that definite integral, the integral function there, is going to be little f of x. That is very powerful because it tells us that the derivative undoes integration. These two symbols will cancel each other out and you'll arrive at f of x. Now, I am sort of hand waving a little bit here when I say those two symbols cancel each other out. Right now, this theorem says, as written, the derivative with respect to x of the integral going from the lower limit of t equals a to the upper limit of t equals x of f of t dt is going to be f of x. So there are some strong restrictions on the statement that the derivative undoes the integral. However, we will massage this a little bit to show you some modifications so that you can take into account any type of definite integral and its derivative. For us to do the proof of this theorem, we're going to have to recall a few major topics within Calc 1. The limit definition of a derivative is going to be used, and the squeeze theorem will be used during this proof. It's not a terrible proof, but it is one that I would not expect a calculus student to do in class, but I would love it if you pay attention during this video. Since we're taking the derivative of that capital F of x, I really want to work with capital F of x plus h and capital F of x, because then we can really transform that into a derivative. As with any good proof, we start with the antecedent, which is that f is continuous on the closed interval from a to b, and capital F of x is told to us to be the integral function t equals a to t equals x of f of t dt. And what we want to prove is that capital F is differentiable and its derivative will be little f of x. So let's go ahead and start with what the heck does the derivative of a capital F look like? Well, we know from the limit definition of the derivative that the derivative with respect to x of capital F is going to be the limit, it's defined this way actually, as h goes to 0 of capital F of x plus h minus capital F of x, all divided by h. Now I'm going to write this slightly differently. Let's say this is equal to the limit as h tends to 0 of 1 over h, and then times the quantity capital F of x plus h minus capital F of x. So far, I hope that this is not mind-numbing or crazy to you. The other thing I need to assume here, it's not much of an assumption, is that x is between a and b, and x plus h is between a and b. And the reason why I have to assume that is because we are really talking about this function f of x being defined on the interval from a to b. And so when I have that little wiggle in x, this little wiggle right here, I want to make sure that that wiggle remains inside our interval. Remember, x is supposed to be between a and b. I want to just have it to where x plus h is also in there. So we're going to go ahead and make that one little bit of an assumption. Not major, but a minor assumption. Let me zoom in and just say that off to the side. So without loss of generality, that's what WLOG means, without loss of generality. Let's just assume that x and x plus h are in that interval. Nothing huge there. If you don't quite follow that, you should be able to, but if you don't quite follow that, it's not a killer for this proof. Then the following must be true. Derivative with respect to x of capital F of x, which we've already written as the limit as h goes to 0 of 1 over h times a bunch of stuff, can be traded out for the integral, because f of x, capital F of x that is equal to the integral from a to x of f of t dt. And so I'm going to trade out both of those expressions right here and here for integrals. One will go from a to x plus h, and the other one will go from a to x. That again should not be anything that's too crazy, because it's just a symbolic change, right? So the integral from a to x plus h of f of t dt minus the integral from a to x of f of t. Oops, that's supposed to be a t. I'm so used to writing f of x, that's just very easy to immediately do that. But f of t dt. So far, so good, right? All I'm doing is trading out symbols. Now, remember, we have recently gone through some properties of definite integrals. And one of those properties we had, let me see if I can rehash it here very quickly, is a summation property, where you can split apart integrals, definite integrals that is. And so let me go ahead and change that, clean that up a little bit. And that's what we're going to do here, is we are going to go ahead and split apart that integral. We could say that the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt is the same thing as the integral from a all the way to x plus h of f of t dt. Remember, the first integral just says, hey, I want the area from a to x. The second one says, hey, continue forward, go from x to x plus h. Well, you could have just said it in one statement, go from a to x plus h, right? So using that equality, I can subtract, let's see, this piece from both sides. If I do that, I will get, so this will imply the integral from x to x plus h of f of t dt would be the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, which is exactly what we have in this bracket right there. So I'm going to go ahead and replace that picture with the single integral from x to x plus h. again, just a symbolic replacement. So this is going to be the limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. Again, hopefully so far you're not lost. We've just compressed this down. We found an expression for the derivative, but we don't know what to do with that expression. Actually, that's kind of a difficult haul at this point. Now, one thing that I am assuming here is that h is positive. There's nothing wrong with h being negative, to be very honest with you, but for this argument here, it's just simpler to say, well, let's suppose that h is approaching 0 from the positive side. So in essence, we are doing a single-sided derivative here, or a single-sided limit, if you will. But that's okay, because we could reform this argument if we really had to argue the other way around as well. So I could, at the end of this, say, well, let's redo the whole stupid proof with h being negative. But for this, let's just assume, without loss of generality, that h is positive. Again, if it's not, we would rebuild the proof once we're done and just change signs, basically. So at the end, really the proof works both ways. So that's why this is without losing any type of rigor. We can just make the assumption that h is positive. And if h is positive, that means that that definite integral is going from x to x plus h, from left to right. Now, I really love this proof because of the fact that it's one of the first proofs you're going to see in mathematics that pulls in a lot of tools. So your toolkit in mathematics right now has a lot of background theory. You know a lot of like the Pythagorean theorem, you know rational roots theorem, you know a bunch of stuff about trigonometry, you know some stuff about calculus. And so we have this whole toolkit that we can access to do proofs. In this specific proof, you're grabbing a lot of things. For example, we've already grabbed the definition of the derivative, right? So we've done that. But here's another thing we're going to grab. We're going to grab the fact that f is continuous, little f, sorry. The fact that little f is continuous. We're going to use that. So right now, in fact. So since little f is continuous, and I'll write that down here. So since little f is continuous on the closed interval AB, and because our interval from x to x plus h is a subinterval of AB, little f must be continuous on the subinterval x to x plus h. Now, I mentioned earlier that I wanted to use the squeeze theorem in this proof, and here's where I get part of the squeeze theorem involved. Since f is continuous, we know by the extreme value theorem, it must reach its absolute maximum and absolute minimum, or at least I should say this, on that closed interval, it must attain an absolute maximum and an absolute minimum. So that's what I've written there. So there has to be a couple numbers between x and x plus h. They can include x and they can include x plus h, but there has to be some numbers on that small interval such that f evaluated at those numbers gives a maximal value and a minimal value. Therefore, there must exist, and I'm just repeating myself here, but I just want to repeat myself with the symbols on the screen. So therefore, there must exist, that's what that backwards capital E is saying, there exists C sub S and C sub L. I'm using those notations because I'm saying a constant, and that's what the C stands for in my brain. S means small, L means large. So there's a C sub small and a C sub large in that interval such that the function evaluated C sub small equals little m, and that is going to be the absolute minimum on that interval. And f of C sub L equals capital M must be the absolute maximum on that interval. Let me just give you, this is not part of the proof, but let me give you a visual off to the side so that you're not terribly confused. We have this subinterval from x to x plus h, and we have a continuous function on that subinterval. It is continuous, which means that from beginning to end, that function must have an absolute minimum somewhere, and I called that point C sub S, that's the x value for that point, and it must have an absolute maximum somewhere on that closed interval, and I called that C sub L. Okay, it doesn't have to be the endpoints. I'm just giving an example here, but there you go. So, and these heights, I'm calling that minimum height on that interval, I'm calling that little m, and the maximum height on that interval, I'm calling that capital M. So all this handwriting off to the right-hand side, you would normally not put within a proof, but I'm putting that there for us to really kind of grab onto so we truly understand what's going on here. But now we can invoke a property of integrals. So again, we're reaching into our big bag of tricks here. And there's a property of integrals that tells us the following. I'm going to write it and then erase it and put it in a proof format. The property that I'm going to invoke here is that if you have a continuous function f and it has a minimum of little m and a maximum of capital M, then the integral, the definite integral from a to b of f of x has to be between little m times b minus a, the upper limit minus the lower limit. And it has to be that has to be greater, your definite integral has to be greater than that, and your definite integral has to be less than the maximal value times the upper limit minus the lower limit. I'm going to invoke that property right now. Therefore, by the properties of definite integrals, our definite integral from x to x plus h. Now, I need to tell you, the upper limit is x plus h, the lower limit is x, so that subtraction will just leave us with h. That's why there are h's here and here, okay? But by the properties of definite integrals, that definite integral is between little m times h and big M times h. Now I've established a triple-sided inequality. I really want to squeeze that integral down. But before I do, let's just showcase one other thing. If you take a look up above, the derivative that we're trying to find the value of, that d dx of f of x, this guy right here, is equivalent to not just this integral, but 1 over h times that integral. That's very important. So it's not equivalent, but it's equivalent to the limit. So let's go ahead and rebuild that limit by looking at that triple-sided inequality. And again, sorry that my screen shears like that. If somebody can just mention in the comments how I can connect my laptop to my PC. Anyway, no worries. It's not that big a deal. Anyway, I want to rebuild that. I just need a 1 over h in front of this integral. So what I'm going to do is divide everything by h. H is not 0. H is approaching 0, but it's not 0. So, and also h is positive, so the inequalities will not flip here. Okay. If h was negative, the inequalities would flip and we'd still be okay. So it's not that big of a deal. That's why without loss of generality, we can still assume h is positive. It's not that big of a deal. So dividing everything by h, we get m is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to capital M. Now remember, little m and capital M are just values that the function takes on at certain points. Again, let me just show that off to the right. Up here, up in your upper right-hand corner, okay, little m and capital M are just function values for f. They're the maximum and minimum values for your function on the interval x to x plus h. For the last part of this, I just need to trade out that little m and that capital M for the function notation that I have right here. Okay, so I'm going to quickly do that. I'm just going to go ahead and write down here, say that little m was f of c sub s, some x value, that's what c sub s is. And that x value, by the way, again, is between x and x plus h. That's going to be critical in a moment. And that's less than or equal to 1 over h integral from x to x plus h of f of t dt. And that is less than or equal to capital M, which is f evaluated at c sub l. Again, c sub s and c sub l are elements or belong in the interval x to x plus h. That's going to be very important because we're going to take the limit as h approaches 0. Remember, this, I'm going to highlight this, this bad boy right here, that is what we want to take the limit of, because that is the stuff that's got that has the inequality. That's the center of the inequality. If we take the limit as h goes to 0, we're really looking at the derivative. So let's go ahead and take the limit as h goes to 0 of all three sides of this. So note, we'll even write it off to the side. Note, oops, that's not supposed to be that color. There we go. Note. The limit as as h goes to 0 of f of c sub s is going to be the same, or maybe I shouldn't say the same, I should say it's going to be f of x, because first of all, f is continuous, and as h tends to 0, that interval right here shrinks down to just x, and so those points get squeezed to become x. I hope that makes sense. I suppose another way I could say it is that as h approaches 0, I'll write it off to the side. As h approaches 0, c sub s will approach x. Okay, well, the limit as c sub s approaches x of f of c sub s, well, that's going to be f of x. Likewise, the limit as h approaches 0 of f of c sub l, well, as h approaches 0, again, c sub l is in this interval right here. And so if h is approaching 0, then c sub l is getting squeezed to become x. C sub l is approaching x as well. So as h approaches 0, c sub l is approaching x, and that's f of c sub l, and so that'll be f of x. So notice both sides of this tend to f of x as h approaches 0. Thus, the limit as h approaches 0 of 1 over h of the times the integral from x to x plus h of f of t dt, that center of this inequality right there, must also be squeezed to be f of x. But remember, that limit, let me scroll up just a little bit here, somewhere in here, there we go. That limit right there, that bad boy, is the derivative. It's the derivative of capital F. So we have just proven that the derivative with respect to x of capital F of x is actually equal to little f of x. Q, E, D, quod erat demonstratum. That is a really, really legit proof. Now, something you need to note, something I'd like to draw your attention to actually, is the number of theorems we had to use to prove this theorem, right? So we started out with our supposition, right? The beginning of this said, suppose f is continuous on the closed interval and capital F is the integral function. Then the derivative of that integral is just little f. It's really what the result was supposed to be. So we started with the definition of a derivative. That was critical. So we had to know that. And then we moved on to using limits and splitting, using properties of integrals to split integrals, definite integrals. And then we started using continuity and the extreme value theorem. And then we used properties of definite integrals again to bound it. And then we used the squeeze theorem. Really, really awesome use of theory to prove something, one of the most important theorems in all of calculus. Now, I have to be honest with you, the way that I have taught it in the past is not the way that I've just written it. So you can see I'm on a very clean page here, and I call this the alternative form of the FTC1. And we call the Fundamental Theorem Calculus Part 1 FTC1 because we don't want to write Fundamental Theorem of Calculus Part 1 over and over again. But here's the alternative form that I use when I teach Calc 1 in a classroom. If you have two continuous functions, u and L, u standing for the upper function or upper limit function, and L standing for the lower limit function, and they're continuous on the closed interval a to b, and differentiable on the open interval a to b, and f is continuous on L of x, the interval from L of x to u of x, where honestly, they don't actually have to be in that order, so this is a little bit of a hand waviness here. And capital F of x is equal to this definite integral right there, that integral function. So all of this is the if part. If all of those things are true, the most important piece being this, well, they're all important, but this part right here, that your integral function f of x has an upper and a lower limit that are not just x's, but functions of x's, then the derivative of that function, which is the derivative of that integral, is going to be the function, this f of x, little f of x right here, evaluated at the top, so evaluate at the upper limit, but by the chain rule times the derivative of that upper limit, and then minus f evaluated at the lower limit, and by the chain rule times the derivative of the lower limit. This is a much more useful form of the fundamental theorem of calculus part 1. And I would prove it here, but I think this video is already long enough. It is not much of a proof, honestly. You just have to use the chain rule because you're taking the derivative of something that used to be an x here, but because it's not an x anymore, you have to use the chain rule to take the derivative of whatever it is now. So that's okay. And then you use properties of integrals to split this integral into the integral from L of x to 0 of f of t dt. I'm sketching out the proof, honestly. Plus the integral from 0 to u of t, f of u of x, sorry, f of t dt. And then you use another property of integrals to rewrite that first integral as the negative integral from 0 to L of x, f of t dt, plus the integral from 0 to u of x, f of t dt. And then if you take the derivative now, so let's go ahead and just pretend that we're asking ourselves to take the derivative of this all along. Sorry that I'm quickly sketching this out. I just don't want this video to spin. I don't want to be on this video forever. When you take this derivative, the derivative of the first, well, it's a negative in front of it. So at least I could pull that negative out of that derivative. So let me do that. And I'll split this derivative as well. So 0 to L of x, f of t dt, plus the derivative with respect to x, integral from 0 to u of x, f of t dt. Now we know the derivative of the integrals, they will cancel out if that was an x, but it's not an x. But that's okay. Now this is a bit hand wavy what I'm about to do. We can at least say, well, if it was an x, we would have gotten f of x, right? That's what we would have arrived at if that was an x as that upper limit. But unfortunately, it's not an x. It's this picture right here. By the chain rule, you have to take the derivative of that picture. And then plus this derivative. Well, again, normally the derivative of an integral, they undo each other and you just get the interior function. But it would usually be evaluated at x. In this case, it's not x, it's u of x. That's okay. But then by the chain rule, you have to take the derivative of that u of x. And this is why that derivative of our integral is f evaluated at the top of the upper limit times the derivative of the upper limit minus f evaluated at the lower limit times the derivative of the lower limit. And trust me, this form will pay you back tenfold if you get to know it quickly. It's a very good theorem to remember. All right, so that's the end of this video. There's a lot of theory and heaviness to it. In the next video, we're going to use this stuff, and hopefully my screen will stop shearing in the meantime.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.